welcome back to the deep dive. Look, before we even get into introductions, I want to jump right in with the absolute key takeaways for today.
Let's do it.
If you take nothing else away from this whole conversation, remember these 3 things about the 3rd week of human development.
Okay, takeaway number 1. I call it the rule of 3.
The rule of 3.
Everything about the 3rd week revolves around the number 3. We are watching the embryo go from a simple 2-layered or bilaminar disc to a complex 3-layered trilaminar disc.
And that process has a name.
It does. It's gastrulation. And it is, without a doubt, the single most important event of your life.
Okay, that's a big statement. So number 2.
Number 2 is the great organizer. We're not just making layers of cells. We're electing a leader.
A leader.
The notochord. It forms this week. And it's not just the precursor to your spine. It's the foreman of the entire construction site.
It's the one telling everyone else what to do.
Exactly. It tells the nervous system where to spark into life. It tells the skeleton where to harden. Without the notochord, there is no body plan. Simple as that.
And the 3rd takeaway.
The 3rd one is a bit of a warning. I call it the danger zone.
The danger zone.
This 3rd week, it lines up almost perfectly with a woman's first missed menstrual period.
So right when she might be realizing she's pregnant.
Exactly. And because this is when we are laying down the absolute fundamentals, the midline, the major axis, it's a period of incredible vulnerability to teratogens.
Things like alcohol.
Alcohol is the classic example. And the damage it can do in this specific window is just catastrophic, structural midline defects.
Okay, so that's our roadmap. Rule of 3, great organizer, and danger zone.
Mm-hmm.
Now, properly welcome in. We are tackling the 3rd week of development.
We are.
And I have to say, looking at our source material, that's Chapter 7, I.B. Singh's Human Embryology, and Chapter 5 in Langman's, it really feels like we've moved past the prologue of a book and into the main plot.
That's a perfect way to put it. It really is the main event. You know, there's this quote from the developmental biologist Louis Wolpert that gets used a lot, but for good reason.
What's that?
He said, "It is not birth, marriage, or death, but gastrulation, which is truly the most important time in your life."
Wow. No pressure then.
Mm-hmm.
For a process that happens when you're about the size of a poppy seed.
Exactly. But think about what's at stake. In the first 2 weeks, it was all about blastocysts and implantation.
Just finding a place to live.
Just securing the real estate. But now, in days 15 through 21, the embryo is actually deciding what it is. It's establishing, okay, this is my head end, this is my tail end, this is my left, and this is my right.
And that gets to the mission of this deep dive.
Yeah.
Because we have these 2 amazing but very different textbooks. I found I.B. Singh to be so clear on the structure. He's all about the where and the what.
He's an architect. He describes the building projects.
Right. But Langman is obsessed with the molecular how and why, the genes, the signals.
And that's our goal here, to synthesize them. We want to take Langman's deep dive into the molecular machinery and layer it right on top of Singh's beautiful, clear architectural diagrams.
So you don't just memorize, this happens on day 16.
Right. We want you to understand why it happens, what signals are flying around, what genes are being turned on and off.
Okay, and the usual disclaimer before we really get into it, this is audio. We're describing a 3-dimensional dynamic process.
It's a ballet.
So think of this as your guide, your ready reckoner.
Yeah.
But embryology is visual. You really, really have to open the books. Look at the diagrams.
Please do. Consider us the commentary track to the movie that is your textbook. You need to watch the movie.
I love that. Okay, section 1, gastrulation,
Right.
the main event. According to Singh, this all kicks off with one structure that appears right on day 15, the primitive streak.
The primitive streak. It sounds like something you'd get in trouble for, doesn't it?
It does. He's got a bit of a primitive streak.
But in embryology, it's the portal of life. It's the entry gate.
So paint the picture for us. We're looking down from above. At the back of this 2-layered disc, the epiblast is the top floor. What do we see?
Imagine you're looking at a flat, oval field. And at the tail end, what we call the caudal end, you see cells in the midline start to pile up. They thicken. They form a linear band.
That's the streak.
That's a streak. But it's not just a flat line. It has topography. It has a landscape.
Right. Singh describes it so well. It's a ridge. And at the very top of that ridge, at the head end, there's a little hill.
That's the primitive node, or the older term is Henson's node, and that's the hill. And right in the middle of that hill, there's a little depression, a crater.
The primitive pit.
The primitive pit. So you've got this whole structure, a ridge, with a groove running down its center, ending in a hill with a pit.
It sounds like a geographical feature. But it's not static. This thing is a machine, and Langman describes it as a site of intense cellular migration, a traffic jam.
A very organized traffic jam. The cells of that top layer, the epiblast, they start marching. They converge on the streak. They migrate toward it.
And when they get there, they don't just pile up higher.
No. This is the magic moment. They reach the groove, and they change their shape, and they dive underneath. They slip below the surface.
Okay, this is the part I really want to drill down into.
Yeah.
Because Langman is so specific about how they slip underneath.
Yeah.
It's not magic, it's chemistry.
It's pure molecular biology.
Hmm.
So normally, these epiblast cells are what we call epithelial cells.
Bricks in a wall.
Perfect analogy. They're like bricks stuck tightly to their neighbors. And the mortar holding them together is a protein called E-cadherin.
E-cadherin is the glue.
It's the glue. As long as that glue is strong, the wall is rigid. The cells can't move.
So for gastrulation to happen, something has to dissolve the mortar.
Exactly. And the solvent is a signaling molecule called FGF8, fibroblast growth factor 8. The cells that make up the streak itself start pumping out FGF8.
And what does FGF8 do to the glue?
It gives an instruction to the migrating cells. It tells them to downregulate the gene for E-cadherin. Basically, stop making the glue.
So the Velcro just comes apart.
Yes. The cells lose their stickiness, they detach, and they change shape from a cuboidal brick to something more like a flask or a bottle.
Yeah.
They become amoeboid, and that allows them to slip right underneath. That process is called invagination.
They dive into the basement, and once they're down there, they start a major renovation project. This is what Singh calls the formation of the trilaminar disc. And the sequence is so important. It's a replacement strategy.
It absolutely is. The very first wave of cells that invaginates, they are the shock troops. They dive all the way to the bottom. They physically invade the hypoblast, that original bottom layer.
And they kick the old cells out.
Kick them out. They push them aside, out to the periphery. They completely replace that bottom floor with a new layer of cells. And we call that new layer the definitive endoderm.
So the endoderm, the future lining of your gut, it's made from cells that used to be on the top floor.
Correct. Then comes the second wave. These cells dive in, but they don't go all the way to the bottom. They fill in the space. They wedge themselves between the top layer and that new bottom layer.
They form the filling in the sandwich.
Exactly. That becomes the intraembryonic mesoderm.
And the cells that are left on top, the ones that stayed put and didn't migrate.
They get a new name, too. We stop calling them epiblast. Now they are the ectoderm.
This was my biggest aha moment from the reading.
Yeah.
I think so many students, myself included, assume the three layers just appear. But they don't. The epiblast is the mother of all layers.
That is the crucial high-yield fact. Ectoderm, mesoderm, endoderm, they all originate from the epiblast. The epiblast is the source of literally every single tissue in your body.
What happens to the hypoblast, the original residents?
They're mostly relegated to forming extraembryonic structures like the lining of the yolk sac. They don't make you. The epiblast makes you.
So now we have our three-layer sandwich. And these new cells, the mesoderm and endoderm, they don't just stay in the middle, they spread out.
They spread out laterally and cranially, sideways and toward the head. They're trying to cover the entire disc.
But, and Singh makes a big point of this, there are two spots where they can't go, two no-go zones.
Yes. Two specific circular areas where the mesoderm does not penetrate. In these two spots, the ectoderm and the endoderm remain fused directly together. The disc stays bilaminar there.
And these aren't just random spots. They have a purpose. They're the future ends of the tube.
Precisely. And the head end, the cranial end, you have the oropharyngeal membrane.
Which will become the mouth.
Right. It'll eventually break down to form the opening to the pharynx. And at the tail end, the caudal end, you have the cloacal membrane.
The future anus and urogenital openings.
That's right. It makes perfect sense from an engineering perspective.
Yeah, if you know you're going to punch a hole there later, why bother filling it with a thick middle layer? Just keep it thin.
It's efficient design,
Yeah.
but it also helps us get our bearings. Even on this flat disc, we now know where the front door and the back door are going to be.
Okay, so we have layers. We have the beginnings of a head and a tail, but we're still a floppy three-layered pancake.
A very organized pancake.
A very organized pancake, but we need some structure. We need a stiffening rod. We need an axis, which brings us to section 2, the notochord.
The notochord. This is the defining feature of our entire phylum, the chordates. And its formation is, well, it's surprisingly complex. I.B. Singh breaks it down into a sequence that's almost mechanical.
It is. It feels like a multi-step assembly from an IKEA manual. It's a lot, for something that just ends up as a simple rod. So let's walk through it. It all starts back at our favorite landmark, the primitive pit.
Right, that little crater in the middle of the node. Cells dive into that pit, but unlike the other cells that spread out sideways,
These ones go straight forward.
straight forward toward the head. They tunnel through the mesoderm like a little boring machine drilling a subway tunnel, and they keep going until they hit a barrier right behind the future mouth.
That barrier is the precordial plate.
It's the one. So
Yeah.
step one is this solid cord of cells tunneling forward. We call it the notochordal process.
Got it. Step one, a solid cord.
But almost as soon as it forms, it changes. It hollows out. It gets a lumen, so now it's a tube, the notochordal canal.
Okay, from solid rod to hollow tube. Simple enough. But then it gets weird. The floor falls out.
The floor falls out. I love that description. The bottom wall of this newly formed tube fuses with the endoderm layer right underneath it.
And then?
And then that section just disintegrates. It disappears.
Yeah.
This is a process called intercalation.
I want to pause on that because the implication is pretty wild. If the floor of the notochordal tube is gone and the endoderm underneath it is gone, you have an open channel.
You do. You have an open connection right through the middle of the embryo, connecting the amniotic cavity on top with the yolk sac on the bottom.
A temporary tunnel.
It's called the neuroenteric canal.
My go-to memory anchor for this is a dumbwaiter.
Yeah.
It's like for a very brief moment, there's a dumbwaiter shaft connecting the attic, the amnion, to the basement. The yolk sac. What's the point of this?
That is a fantastic question that embryologists have debated for a long time. It could be an evolutionary relic from a simpler ancestor. The most likely physiological reason is that it helps to equalize the pressure between those two fluid-filled cavities while the embryo is undergoing this incredibly rapid growth and folding.
But it doesn't stay open for long.
No, it's very transient. If it stays open, that's a major congenital anomaly. But normally, the cells that form the roof of that tube, they get the signal that the show is over.
And they fold back up.
They do. They proliferate, they detach from the endoderm, and they roll up to form a solid rod again. And this is the definitive notochord. It's now a solid cord floating in the middle of the mesoderm.
Wow. So it goes from solid to hollow to an open groove and then back to solid. That is a lot of cellular gymnastics.
It's an incredibly dynamic process.
So now that it's finally there, the solid rod, what is it actually doing? You called it the foramen.
It is the foramen. It has three absolutely massive jobs. Knob number one, it defines the primordial longitudinal axis of the embryo. It's the central pole around which everything else is organized. It gives the embryo its bilateral symmetry.
So it establishes the midline.
It establishes the midline. Job two, it provides the rigid scaffold for the developing vertebral column. The bony vertebrae will literally form around the notochord.
Okay, so axis and skeleton. What's the third job?
The third and maybe most important job is induction. It's a signaling center. It sends out chemical signals to the ectoderm layer sitting directly above it.
And what does it say?
It says, hey you, stop being skin, it's time to become the brain and spinal cord. And that kicks off the whole process of neurulation, which we'll get to.
Before we move on from the notochord, what's its ultimate fate? As adults, we don't just have a rod running through our spine, or do we?
We do, but only in little pieces. As the vertebral bodies, the bony parts of your spine form and harden, the notochord inside them degenerates and disappears.
Okay, so it gets replaced by bone.
Mostly. But in the spaces between the vertebrae, where the intervertebral discs will form, the notochord doesn't disappear. It persists and it expands. And it becomes the nucleus pulposus.
The jelly-like center of the disc.
That's the one. So every time you jump or lift something heavy, the gelatinous core that provides that shock absorption is a direct remnant of your embryonic notochord.
Which brings us to the clinical link. If bits of this notochordal tissue persist where they shouldn't, say at the base of the skull or the tip of the tailbone.
Then you have a problem. You can get a very specific type of tumor called a chordoma.
A chordoma.
They're rare, and they're usually slow-growing, but they can be very difficult to treat because of their location. They arise from these leftover notochordal cells. It's a pathological echo from your third week of life.
Incredible. So we've established the axis from head to tail, the craniocaudal axis, but there's another axis that's maybe even more mind-bending to think about.
Ah, yes. Left versus right.
This is our section 3, and it's almost a philosophical question, isn't it? The embryo, at this stage, looks perfectly symmetrical. A mirror image. But my heart is on the left, my liver is on the right. How does this ball of cells figure that out?
It's one of my favorite stories in all of biology. Because you're right, if you were just building a mannequin, you'd make it symmetrical. It's easier. But Biological function, like pumping blood or digesting food, requires asymmetry.
And Langman tells the molecular detective story here. And it all comes back to our hero.
The primitive node, the great organizer.
The Spearman organizer, yes.
So it turns out the cells on the ventral surface of the node on its underside within the pit are special. They have cilia.
Like little hairs.
Tiny hair-like projections. Now, when we usually think of cilia, we think of them in our airways, beating back and forth to clear mucus.
Right, a sweeping motion.
But these nodal cilia are different. They don't just wave back and forth. They beat in a rotary pattern. They spin clockwise.
They spin? And what does that do?
It creates a current, a tiny but very important vortex in the fluid surrounding the embryo. And because of the way the pit is shaped, this spinning creates a consistent directional flow of that fluid. It pushes the fluid toward the left side of the embryo.
So there's a leftward current, the nodal flow.
Exactly. And that fluid isn't just water, it's full of signaling molecules. And Langman singles out two key ones, serotonin, or 5-HT, and another growth factor called, appropriately, nodal.
And because of the current, these molecules get swept to the left.
They do. They get pushed to the left side of the node, and they accumulate there in a high concentration.
So now you have a chemical difference. High serotonin on the left, low serotonin on the right.
And that chemical gradient is the first domino. It triggers a whole cascade of gene expression. The high serotonin on the left activates the gene nodal, and nodal eventually turns on what Langman calls the master gene for left-sidedness,
Which is?
a transcription factor called PITX2.
PITX2.
If a cell expresses PITX2, it has its identity. It knows, I am on the left, I must now build left-sided structures, like the heart's chambers and the stomach.
So what's happening on the right side to keep it right?
Well, two things. First, it's just not getting that high dose of serotonin. And second, there's an enzyme on the right side, monoamine oxidase, or MAO, which actively breaks down any serotonin that might drift over.
So it's actively keeping the right side a low serotonin zone.
Exactly. And other genes, like one called SNAIL, are expressed on the right to help define right-sided structures, like the large lobe of the liver.
I have to stop and just marvel at this.
Uh-huh.
The entire asymmetric layout of my internal organs comes down to microscopic hairs spinning in a puddle when I was the size of a pinhead. It seems so fragile.
It is incredibly fragile. And we know this because of what happens when it goes wrong.
Okay, let's bring in the clinical vignette.
There's a genetic disorder called primary ciliary dyskinesia, or Cardiganer syndrome. And in these patients, their cilia are defective. They're immodal. They don't spin.
So no current,
No.
no nodal flow.
No flow. The serotonin and nodal molecules just diffuse randomly. There's no gradient. The decision of left versus right becomes a coin toss.
And the result of that coin toss?
About 50% of the time, you get situs inversus, a complete mirror image reversal of the organs.
So the heart is on the right side.
Dextrocardia, yes. The liver's on the left, stomach on the right. And often, a person can live their whole life completely unaware of it.
Until they get a chest x-ray for a cough and the technician does a double take.
Exactly. And Langman adds a really fascinating pharmacology alert here related to serotonin.
I saw that. What if the mother is taking an SSRI, an antidepressant that specifically targets serotonin levels during this critical third-week window?
It's a valid theoretical concern. The mechanism is plausible. If you flood the system with serotonin, you could potentially overwhelm that delicate gradient. Animal studies have shown it can cause laterality defects.
And in humans.
The data is much more complex, and it's not a definitive link, but it highlights just how sensitive and crucial this very specific biochemical signal is at this very specific time.
Okay, that's fascinating. From the axis, let's move to the map. Section 4. Fate maps and mesoderm differentiation. This is the idea that a cell's destiny is determined by where it enters the primitive streak.
Location, location, location. It's true in embryology, too. You can essentially draw a map on the surface of the epiblast that predicts what each region will become after it invaginates.
So let's say I'm a cell entering through the very top, through the node itself, the VIP entrance.
You're destined for greatness. You become the notochord.
Okay. What if I enter just to the side of the node?
Then you become the paraxial mesoderm.
Which goes on to form the somites.
The somites, yes. The building blocks of the vertebrae, the ribs, and the muscles of the back.
And if I enter further down the streak, in the middle...
That's the intermediate mesoderm. That's your urogenital system, kidneys and gonads.
And if I'm late to the party and enter way at the caudal, tail end.
Then you become the lateral plate mesoderm. That's a bit less glamorous. It forms the body wall, the lining of the body cavities, and a lot of the circulatory system.
But it's not just about location. There's a chemical war going on here, isn't there? Langman describes this battle between ventralizing and dorsalizing signals.
There is. It's a constant molecular tug of war. So, you have to understand that the default setting for mesoderm is to become ventral tissue.
Belly side stuff.
Belly side stuff, exactly. Body wall, blood vessels. And this is driven by a powerful protein called BMP4 bone morphogenetic protein 4. BMP4 is secreted everywhere. It's basically shouting, everyone become ventral.
So if BMP4 was left unchecked, we'd just be a blob of belly tissue, no spine, no brain.
Precisely. We'd have no back. But the node, our organizer, fights back. It secretes a cocktail of BMP antagonists.
Blockers.
Yes, blockers with these fantastic names. Noggin, cordon, and follistatin.
Noggin has to be one of the best protein names ever.
It really is. And what these molecules do is they bind directly to BMP4 and they inactivate it. They soak it up like a sponge.
And where do they do this?
Right down the midline. They create a BMP-free zone in the dorsal part of the embryo. And by blocking the ventral signal, they allow that tissue to follow its true destiny.
Which is to become dorsal structures.
Yes. The notochord, the somites, and critically, the neural plate. The spine and the brain can only exist because the node protected them from being turned into belly.
The node is the override switch.
It is the override switch that allows for all the interesting complexity to happen.
And that leads us perfectly into the result of that complexity. Section 5. Neurulation. The birth of the nervous system.
Yes. The notochord is now in place. The BMP4 has been blocked in the midline. The stage is set.
So the notochord, the foreman, now speaks to the ectoderm layer, sitting right on top of it.
This is a classic example of induction. The notochord sends out signals, including noggin and chordin, and they instruct the overlying ectoderm to thicken. This slipper-shaped patch of thick ectoderm is now called the neural plate.
And this is where the famous folding begins. We go from a flat plate to a tube.
We do. The lateral edges of the neural plate begin to elevate. They rise up. These are the neural folds.
And as the edges rise, the middle part dips down,
forming the neural groove.
I always picture it like folding a piece of paper to make a taco. The two sides curl up.
The taco is a perfect visual. The neural folds, the edges of the taco, continue to curl up and toward each other over the groove. Eventually, they meet in the midline.
And they stick together.
They touch and they fuse. And the moment they fuse, that strip of tissue detaches from the rest of the ectoderm and sinks down. And just like that, you've turned a plate into a tube. The neural tube.
But this fusion, it doesn't happen all at once on the whole length, does it? It's more like a zipper.
It is a zipper, a bidirectional zipper. The fusion starts first in the cervical region, the future neck area, around the fifth somite.
And then it zips in both directions from there.
Exactly. It zips cranially up toward the head and simultaneously zips caudally down toward the tail.
Which means for a short period of time, the two ends of the tube are still open to the outside world.
Yes, and those openings are called the neuropores. The cranial neuropore at the head end and the caudal neuropore at the tail end. They allow amniotic fluid to circulate inside the developing neural tube, which is important for nourishment before a proper blood supply is set up.
But they absolutely have to close, and the timing is non-negotiable.
It is critical. The cranial neuropore at the head end must be closed by day 25. The caudal neuropore, the tail end, must close by day 27 or 28.
This comes right back to the danger zone. If those zippers don't close on schedule, they never will.
That's correct. And that failure to close is the direct cause of neural tube defects. If the cranial neuropore fails to close, you get anencephaly, a failure of the brain to form. It's not compatible with life.
And if the caudal end fails to close?
You get spina bifida. And this is precisely why folic acid supplementation is recommended before a woman even tries to conceive. By the time she misses her period around day 28 and realizes she might be pregnant.
It's too late. The neuropores should already be closed.
The window for prevention has already passed. It's a sobering clinical reality.
It really is.
Yeah.
Now, during this whole zippering process, there's a special group of cells that I find absolutely fascinating. The neural crest cells.
Ah, the great explorers of the embryo.
That's what they are. So as those neural folds are rising up and meeting in the middle, the cells at the very tip, the very crest of the fold, they do something different.
They break the rules, they don't join the neural tube, and they don't stay behind as part of the skin ectoderm. They detach.
And they go on a journey.
They undergo another one of these transformations, an epithelial to mesenchymal transition, and they start migrating. And they go everywhere. Absolutely everywhere.
I've seen them called the fourth germ layer.
It's a totally fair description given their importance. They migrate into the face to form almost all the bones and cartilage of your face and jaw.
So my face is made of neural crest cells.
A large part of it is. They form the melanocytes, the pigment cells in your skin. They form the entire adrenal medulla. And critically, they form the entire peripheral nervous system, all the ganglia, all the sensory neurons, and the nervous system of your gut.
So the neural tube becomes the central command, the brain and spinal cord.
It stays home.
And the neural crest cells are the scouts and messengers that go out and wire up the rest of the body.
Exactly. They are the nomads that integrate the entire system.
I want to make sure we don't skip over section 6, the supporting structures, the allantois and the chorionic villi. They can feel like footnotes, but they're so relevant to the danger zone concept.
They are absolutely vital to the story. Let's start with the villi on the placental side. While all this incredible folding is happening in the embryo, the placenta is in a frantic race to establish a blood supply.
It's evolving.
Rapidly, we see the chorionic villi evolve from primary, which are just columns of trophoblast, to secondary, when a core of mesoderm invades them, to tertiary.
And tertiary is the crucial step.
That's the game changer, because in tertiary villi, blood vessels and capillaries form inside that mesodermal core.
And those vessels connect back to the embryo.
Yes. By the end of the 3rd week, around day 21 or 22, the embryo's own heart starts to beat, and it starts pumping blood out into these villi. For the first time, you have a functional circulatory connection.
And that connection is a double-edged sword.
Absolutely. It's the lifeline that delivers oxygen and nutrients, but it is also the highway for teratogens. Just as the neural tube is zippering shut, the mother's blood and anything in it, like alcohol or certain medications, suddenly gains direct access to the embryo.
So the establishment of the tertiary villi is the biological event that opens the door to the danger zone.
It coincides perfectly with the period of maximum susceptibility to structural defects. It's the mechanism.
And very briefly, the allantois. It's this little sausage-shaped outpouching from the yolk sac.
Yeah, it extends into the connecting stalk. In birds and reptiles, it's a huge sac for storing waste. In us, with our fancy placenta...
It's kind of rudimentary.
It is, but it's not useless. Its blood vessels are critical. They become the umbilical arteries and vein, and the structure itself persists as the urachus.
A fibrous cord that connects the bladder to the umbilicus, the belly button.
Exactly. And if that cord doesn't seal off properly after birth...
You can get a urachal fistula, we see it in pediatrics, a newborn with urine leaking from their belly button. It's a direct physical reminder of a structure from the 3rd week of life.
It's embryology presenting in the clinic.
Which brings us neatly to our final section, section 7, the big clinical correlates. We've talked about a few, but there are some classic pathologies that are born exclusively in this week. The first is a direct result of the primitive streak not knowing when to quit.
Right. The streak's job is to make the 3 germ layers. It's a stem cell factory. But by around day 26, its work is done. It's supposed to regress and disappear completely.
But sometimes it doesn't.
Sometimes remnants persist, and those cells are pluripotent. They can become anything, so they just keep building.
But without a plan.
Without a plan, they form a giant tumor at the base of the spine, at the coccyx, a sacrococcygeal teratoma. It is the most common tumor in newborns.
And because the cells can make anything, the tumor contains everything.
It does. When pathologists examine them, they find a chaotic mix of tissues: hair, teeth, bone, muscle, sometimes bits of brain or intestine. It's a biological monster in the original sense of the word, a disorganized creation.
That sounds terrifying for new parents. Is the prognosis usually good?
Thankfully, yes. Most are benign and can be completely removed with surgery, but it is a very stark reminder of the incredible creative power locked inside the primitive streak.
Okay, then there's holoprosencephaly. This one really drives home the danger of alcohol.
It does. This is fundamentally a defect of the anterior midline of the germ disc. We now know that a high dose of alcohol during this 3rd week is cytotoxic. It kills cells, and it seems to preferentially kill the cells in that anterior midline.
And those are the cells that are supposed to tell the forebrain to divide into 2 hemispheres.
Exactly. So if those inducing cells die, the forebrain fails to cleave. It remains a single, undivided vesicle, holoprosencephaly.
And since the face develops in concert with the brain,
the face collapses toward the midline as well. You see the eyes set too close together, hypotelorism. In the most severe and tragic cases, the 2 eye fields can fuse into a single central eye, cyclopia.
It's just devastating.
Yeah.
And it's a direct failure of the basic body plan being laid down in this week. At the other end of the embryo, we can have a failure too. Cyanomelia.
Mermaid syndrome. This is essentially the opposite problem of the teratoma. Here, the primitive streak stops working too early, or it just doesn't produce enough mesoderm in the most caudal region.
Not enough raw material for the back end.
Not enough mesoderm to form two separate lower limb buds, so the legs are underdeveloped and fused together.
It is striking how our ancient myths, cyclops, mermaids, are almost perfect descriptions of these specific embryological errors.
It's very likely that rare observations of these congenital anomalies in ancient times were the origin of those myths. Embryology gives us a biological basis for the monsters of our stories.
We have covered a huge amount of ground, from the dissolving cellular glue of gastrulation, to the spinning cilia of the node, to the delicate zippering of the neural tube. How do we wrap this up?
I think we go back to the idea of a bridge. The third week is the bridge between being a simple collection of cells and being a body. We entered this week as a flat, two-layer disc. We leave it as a three-dimensional, tube-like organism with a central axis, the beginnings of a nervous system, and a tiny beating heart.
Gastrulation provides the raw materials, the endo, meso, and ectoderm.
The notochord draws up the architectural blueprint.
And neurulation begins construction on this central control tower.
That's the perfect summary.
And for our final provocative thought, I want to go back to what you said about fluid dynamics.
It's the idea that always stays with me after teaching this topic.
Just take a moment and think about the sheer fragility of your own body plan. The fact that your heart is on the left and not the right was decided by a microscopic current in a tiny pool of fluid.
A current driven by little hairs spinning around. If that fluid had been a tiny bit too thick, or the cilia a bit too weak, or if a random chemical signal had been off,
You might be a mirror image of yourself. Or worse. We think of our bodies as being determined by this robust genetic code, but right here, at the most critical moment, it's also about physics. Fluid dynamics.
It is. Which makes you wonder, doesn't it? What other random physical forces or tiny fluid shifts played a role in determining who you are today?
That is a question for a much deeper dive.
Indeed.
For now, here is your call to action. We've used analogies like tacos and zippers, but you cannot learn this with your ears alone. Please, go open Langman's Chapter 5. Look at the cross-sectional diagrams of the embryo folding.
You have to see it. Watch that flat disc curl up and form a tube within a tube. Once you see that transformation visually, it will click in a way that words alone can't achieve.
Thank you for listening to this deep dive into the third week. Join us next time as we continue to build the human body, one complex layer at a time.
See you then.